Welcome and good morning to the second session this morning. My name is Grunwald from DN Systems from Germany, and I'm going to present some new things in attacks against RFID systems. We have heard a lot about RFID, and who of you guys attended my talk 2 years ago to the RF dump? Okay, not so many. We have not been lazy the last 2 years, so we are able to develop and push RF dump more forward. 2 years ago, I got a lot of press quotes and from spokesmen from the RFID lobby. They're telling us, oh, this is not possible. The unencrypted text will be encrypted. They will be secure. We are going to encrypt any data. And now let's have a look to encrypted RFID tags, exploits, new ways to exploit their systems. We have a short look to the unexpected risk to the middleware. We are talking a little bit about reader emulation and soft tags, we call it, with RF dump, and how to exploit and attack RFID systems. And first, I'm going to give you once again a short overview. What is RFID? And in the big case, RFID stands for a whole bunch of communication protocols. Radio frequency identification is much more than EPC, is much more than a RTD, a RFID passport. It's much more than an access control card or a pay card or your credit card. It's, in general, the wireless transmission of information between transponder and reader without any visibility. And it enables, in most times, bidirectional transfers. So you are able to read and write the RFID tag. And the transponder or tag can be attached, embedded, or implanted. And it allows you to do automatic correlation between objects and saved data. So we have a lot of generic terms if we are looking to RFID. Often RFID is used as a generic term for the complete infrastructure. This infrastructure depends on different parts. We have a transponder, also known as RFID chip, tag, label, wireless label, or simple RFID chip. A reader, but in most cases, the reader also allows you to write to the tags. We have some middleware. Normally, the middleware is going to connect the reader to the server. We have communication infrastructure and integration with server farms, data warehouses, services, and supporting systems. So there are different types of RFID. We are going to sort them on the depending read distance. We have short read or short range RFID solutions. For instance, the ISO 14443A and B. It's operating on 13.56 megahertz, or the low frequency stuff like you implant in your cat or the very chip. It's 125 to 143 kilohertz. And it's using the electric and the magnetic field for exchanging the information. We have mid-range solutions. The read range is up to 5 meters. Typical is ISO 15693. And it's also operating on the frequencies like the short-range stuff, and it's using only the EM field. And we have long-range RFID solutions, like demonstrated the last year, and it's operating on higher frequencies. So there are transponders out in the field, and we have different kinds of transponders. This specific type of transponders, they are only transmitting a unique ID, like a serial number. They are only passive. They are used sometimes for identification. They are used for tracking, for e.g. fast track, and they are only operating in clear text communication. We have transponders that are able to store data. It's pretty much an EEPROM or EEPROM. So most of them are passive, some are active. That means they are carrying a small battery, and they are battery powered for higher range. The best known is the EPC label. We have smart labels, and most of them are using clear text communication. Some are using encrypted communication. And we have transponders that act like a smart card interface. Most of them are passive, some of them are active, so you don't want to change a battery before you can cross the border for your passport. So they change to use a passive smart card interface. Some of them are used for access control systems, For instance, the MyFair Deathfire, and they are normally using encryption, authentication, and encrypted communication. So we have heard a lot of generic attacks, so I will just give you a short overview for who of them who were just sleeping the last presentation, either in the room or in your hotel bed. So sniffing the communication between the transponder and the reader, so you can counterfeiting of communication. You can obtain a user ID, user data, and metadata. You can perform basic attacks to structures and tags. And for instance, you can do a replay attack to full access control systems. Also, you can counterfeiting the identity of a reader and do unauthorized writing to the tag. For instance, change the user ID or with manipulation of the administrative block. So you are able to declare false identity. So the UID must be readable in clear text, and manipulation of product groups and prices, as presented 2 years ago. And you are able to manipulate the data directly stored at the transponder. So you are able to manipulate the data and the metadata. You can logically swap objects or logical duplication of objects in your supply chain, for example. Or you can deactivate the transponder to disable the traceability of objects or disable the visibility of objects. And you can do attacks against structures in the middleware and backends of manipulating data and structures. For instance, you are able to inject malware into backend systems or middleware systems, as shown at the last presentation, for instance, database worms or manipulations of backend systems. You can also always perform an attack against the infrastructure. You are able to jam RFID frequencies. The most of the RFID frequencies are used the ISM band, so you can just go to a police store and buy out-of-band police jammer to shut down a supply chain. You are able to do attacks against the anti-collision mechanism like discussed in the RSA paper, or you can prevent reading the tag if you're jamming the frequencies, doing a simple denial of service attack against the RFID systems, or shut down the whole production, sales, or access. If this type of tags controlling your production cycle or used for your logistics into your warehouse or your stock. Now let's come to the interesting things. We have done research on the last couple of months. Encrypted RFID. So the most of the attacks, as quotes from spokesmen from the lobby and industry, are shown, oh, this is only possible because we are not using encryption. The new RFID attacks will utilize encryption, so you cannot do sniff, you cannot do clear text communication, and you cannot break in two. This type of cards are pretty common for your access control system to drive into your garage, or if you check in a nice hotel, you get some sort of cards as access control. Or it's used for data center access control, so for more risky parts than normal clear text stuff. The technology is based on ISO 14443, and it's operating on the 13.56 megahertz frequency. The MyFair tags, there are two types of MyFair tags. We have the MyFair standard. This is proprietary high-level protocol, and Philips proprietary security protocol used for authentication and ciphering. And we have the MyFair Lite. This is the same tag without any type of encryption. You only have the memory from the tag. And we have the interesting things like MyFair Pro, MyFair Pro X, and SmartMX. These are fully compliant to the ISO 14443 standard. There are different types, and these different types of tags offers you different memory space. This memory is protected by two different keys, the A and the B key, and each sector. So the card is segmented in different sectors, and each sector could be protected with one of these keys. Normally, it's pretty secure. So we have tried to brute force attacks. With this key space, it takes more than 22,000 years, In fact, you need to initialize the tag and you need per round with a brute force Perl script 25 milliseconds to run a brute force attack against these keys if you're using one RFID reader. In case these keys are shared secrets, so you can use more than one. You can use, for instance, 1,000 readers. But it didn't help much. If you share the key space and you make a distributed attack, you still need 226 years. So something like a botnet or something like this is necessary, and it's a huge problem because most of the PCs outside doesn't have RFID reader and doesn't have the cards, so it's not difficult, or it's difficult to clone these cards, to distribute the cards to millions of machines and trying to break them. So we need a different approach. Unfortunately, Philips put all information under NDA. And if you're doing security research, you're not interested to sign any type of NDA. So what we actually did is we got some RFID software and used the Unix command strings. Who knows the strings command? You know what's happened if you use the strings command? You get the 0-byte terminated strings out of the program. And the next thing is we looked at the results and found some strings that exactly matched the key length used to get access to a sector. So, and once again, Google is your friend. Every developer has a Google desktop installed. It's very popular, especially at smart card developers. And what's the problem? Oh, they're all lazy. They don't want to enroll passwords to access. So they're putting all this secret information into a special directory where no one can access. Unfortunately, Google search was installed on this machine. So the developer was looking for some information. He signed the NDA. He got the special URL personalized for him. No one else can access. And thank you to Google, the world got it. So look at the results. We got a whole bunch of keys and also the most information that's just under NDA, but it's public available through Google search. Okay, we got some keys, we got some information. Oh, wait a minute, we also got the data sheets. And we got the default keys, we got more than 60 keys from example applications. Even without any type of protection, you can access with a 0 key. So, what will be the next step? Oh, there's a nice document. It's called MAT, and it is really MAT. This is the MyFair application directory. This is a PDF that shows the MyFair tag, and Philips tried to standardize something. So they put something like an application identifier into each MyFair tag. And if you're doing an application like a ski pass or a ticketing or counting or something like this, you can classify your layout, you can classify your tag, how is it formatted, how are the sectors formatted, and how is it working, and put it into application directory. Something like ticketing has a specific entry, something like access control or pay cards. So, and what we found is in this data sheets, we got a lot of sample layouts pointing to these examples. These sample layouts includes different keys of tag and memory layout and the complete data structure for ticketing, access control, or online payment. So, and you know, developers are really lazy. So we have checked a couple of these cards and more than, 75% use default keys. So something like, let's compile a chiplet. And the programmers are not using only the example layouts, they're also using the example keys from the data sheet. So let's do attacks to the tag. Now, what's possible? We can do dictionary attacks that speed up this process. We can try this dictionary attack with all possible found keys, and some developers are really smart. They make small variations of the keys. So we can use a dictionary with a smart brute force attack to the text, it's possible. So, and one big problem of the design is I've never seen a logout or a false login counter. So if you reset the tag, you can get access once again. And a delay for a false key does not exist. Normally, we would expect with a crypto and a well-designed crypto mechanism, after 4 or 5 false logins, you got a delay about 5 or 6 minutes. But these tags are passive. They don't have a clock or anything. So if you just repower them and make an actual reset of the smart card, you can get access once again. We are also possible to do attacks to the backend. For instance, the memory of the ISO 15693 tag acts like a normal storage. It's nothing more than a small USB drive or something like this. We use, of course, RFDump. It's our software. It could help you to manipulate the data like a hex editor. So you can do SQL injections or other attacks are also possible. Yes, what's happened if we got read-only tags? So we read it with RFDump and put the manipulated one to a new tag. That's read-write. Checksums and some implementations use the UID as a mirror block in the user data. This must be changed, of course. And if the block is encrypted, the sector key must be broken once again. I'm going to skip this. And we have here a possible way how to break into a RFID supply chain. We have an event manager, we have information server, middleware. You can also transport exploits to your ERP or CRP systems right into the backend. And one big problem of the most tags is they just have a memory warp. So if you try to read multiple pages, you get a multiplier of this page back. So it appears that you have unlimited space to the tag. So RFDump use, for instance, a tag database to avoid reading over the boundary. But normally, the reading is event-driven. So they start reading up to end of field. And as always, input is unchecked in all implementations we have seen. So this is one small denial of service attack with a C-string. And what we are going to see is we have the production data and the C-string terminated by zeros. Just imagine what's happened if you remove it. You got an unlimited. Now there are some additional ideas. There are patents outside in the US. We are no longer doing binary structures and putting binary structures into RFID tags. We're using XML. And of course, it's also possible. If you just fill your tag with RFDump with opening tags, that's it. Another idea that's going to be supported with RFDump, we call it soft tags. It's an emulation of a complete system. So the backend of RFDump can act like a reader and a writer. We do a serial emulation of an ISO 15693 tag. It's really useful for testing backend and middleware, and it reads backups from real tags and manipulation of any UID, user data, or administrative block is possible. Now, first, before we coming to the e-passport, I would like to show you some demonstration of the new version of RFDump that's going to be released in a, it's going to be released in a couple of days. I'm still not with this Microsoft stuff. Okay, we have here the new RFDump. We are going to release, it's a Linux application. So with this Linux application, we are going to ship with the RFDump 1.4 version a VMware image, so everyone can get to his favorite Vista, Microsoft Anyway desktop, download a VMware player, and can get one out of his desktop, this special small Linux version of RFDump. It has some additional features, like my last presentation. You can set up the preferences. You have the cookie. You can now use the cookie also for 14443 tags. You are able to read a tag at once. If you start scan, it's just getting all data. It identifies the tag ID. You got the MyFair tag, and it starts reading the page until it hits the boundary. After the page is read, we have the possibility to make the manipulation as known with our classical IFDump. You have an ASCII. It's something like a hex editor for RFID tags. And you can save the layout and load it into the emulator, change anything you want. And we have this new, really cool new feature. You can make a brute force attack trying to break the MyFair key. And the next version is going to release in this next weekend. We'll have the dictionary as well to get the encrypted RFID in the same manner like the unencrypted RFID. Okay, and I see we have half our time. Let's start to another research we have done regarding RFID. I'm just going to turn this off. My first question is, are any Europeans here using one of these nice fancy RFID passports and would like to come to the podium for a demonstration? Okay, I applied for a new passport 2 weeks before the BlackHat and I got one, so we are going to do this demonstration with my own passport. Let's have a short overview over the e-passports. MRTD, Machine Readable Travel Document, also known as Electronic or e-passport. It's specified by the ICAO. This is the International Civil Aviation Organization. Normally, they are doing specifications, how many noise can come out of an airplane engine and what's acceptable and what's the wingspan and what type of airplanes we have. Now they are trying to make IT security. You can imagine what happened. They decided to make an involvement of a global basis. We have this new e-passport from Germany. The tag is embedded into the cover. After my presentation, you can look in front here. And it's produced by Bundesdruckerei GmbH. It's a company owned by the state. And it stores the passport data and biometric information on a RFID transponder. There are also alternative storage methods like a 2D barcode. So if you don't want to use an RFID, they can use a 2D barcode to store the information on a normal readable page. And it's a common standard for interoperability, and some features are mandatory, others are optional. Here's an example with a 2D barcode and the MRZ. MRZ stands for Machine Readable Zone, and this Machine Readable Zone is the key for the basic identification. We will cover this a little bit later on. So let's come to the Machine Readable Travel Document data layout. So they defined also all terms new. So they have now the logical data structure, or called LDS. The data is stored in DGs or data groups, not files like anyone else would call it. We have the data group 1. This data group 1 includes the MRZ information and is mandatory. We have the data group 2. This is holding an image portrait and a biometric template. This is also mandatory right now. And we have optional data groups like the DG3 and DG4 to hold additional fingerprints and iris image. We have the security object data, and we have the EFCOM. It lists what data groups are existing. All data is stored in bare encoded RSN1, and the data group 4 to data group 2 or 2 to 4 use CBFF. It stands for Common Biometric File Encoding. It is also a public standard. It's ISO 19785. Some features. So normally, any RFID chip, any 14443 transponder has a fixed unique serial number. This number is necessary to do anti-collision if you have more than one transponder in the field. After the first design of the ICAO, I got a lot of pressure from privacy groups. So to prevent tracking of the owner without access control, they decided every time if the passport tag gets activated, he is presenting a new unique identifier. So it's now not truly random, but some type of random. The problem is The ICAO machine-readable travel document specs don't require unique serial numbers. And some countries will generate random serial numbers, others won't. We have passive authentication. This type of passive authentication is mandatory for all passports, and it's the method of proof of the passport, and the files are signed by the issuing country. The inspection system has to verify the hash of the data groups. Each security object data contains individual signatures for each data group, and the EOF SOD is signed itself. The document signer public key from the PKD bilateral channels, and the document signer key can be stored directly on the passport. Useful if the country root certifying authority is publicly known. So this is the structure. So they are building actually hashes over each data group. All these hashes are stored and also hashed in a EF-SOD, and the EF-SOD is signed by the issuing country certification authority. Now we have something more. It's called basic access control. This system is to permit access to the data after the inspection system is authorized. So authorization to the machine-readable zone. To get the data actually out of an RFID passport with basic access control, you need the 9-digit document number. In many countries, it's the issuing authority and the incrementing number. That's the way, like the Netherlands passport get hacked, because they are issuing 5,000 passports per year and just incrementing the number. So they'd start at some known value and just make a brute force. Then we have the date of birth, and we have the 6-digit expiry date. And the 16 most different bytes of the SAH hash over the MRZ are used as key on the SM for secure messaging. So, by the way, who gave his document number at the check-in at the Caesar's Palace? Do you imagine what's possible? Now, someone breaks into the computer at the Caesars, get all the document numbers, and can now easy brute force your machine-readable travel document. We have also a method that's called extended access control. This is optional because some countries are not interested to sharing biometric information with others. So it's not standardized, and it's implemented by individual issuers, and it means that the content in the DG3 and DG4 is encrypted and can be only accessed with one of the countries who allowed shared access. For this reason, they are planning a huge PKI. Each issuer operates a self-control certification authority. The signer keys are diverted from the CA root, and the public keys are distributed by ICAO PKI distribution, so everyone can verify. Unfortunately, they had just forgotten to make a CRL. So if one country is losing the keys, the complete system is doomed. So let's come to a specific part of this presentation. We have spent some time to make it possible to clone these passports. So we have here some standard dual interface tags. They are using a JCOP. This is a BlackHat operating system. And with some additional programming and reading the standards, they could act as a machine-readable travel document. The data could be retrieved from an issued passport, and personalization is possible through a special shell at the backend to RFDump. And let's check how the cloned passports behave. For this reason, I got a small tool. It was developed by the German state, and it's called Golden Reader tool. So let's start the Golden Reader. And I've brought, this is my own passport. Please excuse me, there's a rule. We have to look in a specific way on this passport because otherwise the biometric will not work. So I'm putting it on, telling them, reading basic access control, pointing to my MRZ. I've just programmed it. There are two ways I can install a reader, like to swipe it through a keyboard here. It's supported, or I can just punch it in. Please place passport. And now it starts reading and getting all the information out of my actual passport. So now you can see it's checking the data groups. It's checking the SOD message digits. It's checking the certificate. It's checking the signature, and it's checking the hash. Certificate status and certificate verification are not implemented, so it's not checked. COM integrity is checked. Reading data group 1, reading data group 2, reading hashes, and that's it. Now let's come to the interesting facts. So we want to see something more than only this one. So I'm starting a small tool. This is called a smart card shell. Okay, I got it. So with an R, I sent a reset. That's a smart card protocol. And I can start scripts to perform operations. So what this script is actually doing, it's making basic access control, accessing to the passport with the ICAO protocol, and just dumping the whole context of the smart card just as 4 different files onto my hard drive. After they are dumped, I'm using one of these normal available smart cards. It costs 15 euros, about $20. You can buy it via the web at IBM Zurich. Put it onto the reader. Starting a personalization tool and just writing the data, including the ICAO layout, directly into the corresponding new chip. I need to remove it, so I need to reset the cards. This card has application loader, it has flash memory, it needs to boot, so I need to put it off, put it back, and now let's check our result with the golden reader once again. Oh, who is that? Okay. Am I so boring? Or was the party so huge? Hello, wake up. Okay. But I can do just more fancy stuff with this. I can just use someone else's data. Now, I will join a new country. All are so evil to me, so I'm going to join to Utopia. So I'm just copying someone else's data directly to the file, overwriting all files, making a reset to the card. Okay, here we are. And you can see it's a Jacob 41 version 2.2. And now I want to just try what's happened. So I'm taking this passport, I'm using a hammer, deconnecting or destroying the microchip, and putting a new one into the passport, like this type, and putting my new passport back onto the inspection system. And now what's happened? Oh, this is obviously not me. Okay. Um, let's go back to the presentation. So, we have some security issues. First of all, the UID from this tag could be changed from any tag. So with this type of tags, if we have an access control system and it's using only a unique identifier, this tag has a small algorithm generating a random number and sending it as unique identifier. So if you change it, you can fool out any ISO 14443 access control systems. They only rely on a unique identifier. The next thing is the passport tag could act as access control tag, and the biggest risk is that the manipulated data group, and if we have some more time, I would love to present you how it's able to change it. The manipulated data group could crash the reader and the terminal. Unfortunately, they made everything wrong that they could be. So they don't understand how ASN1 is working, so they tried to re-implement it. They make it not correct, so you cannot pass it against the normal ASN1 library because you have to do exceptions. They are breaking the standards. It's no longer possible to validate it against ASN1 legs, and so on. Each programmer has to reinvent the wheel and can trap to ASN1 parsing errors. You have problems with the data, you have problems with the data size, you have problems, the picture is encoded in 4 different encodings. We have an ASN1 encoding on top, I can demonstrate this. We have an ASN1 encoding. On top of the ASN1 encoding, we have this biometric file format. Included in the biometric file format is a JPEG 2000 and it's a biometric template, and everything is encoded in a TLV encoding on the smart card. So in fact, this means how many mistakes could be done and how many ways to make a buffer overrun or to make an exploit to inspection system. And even if the cryptography is secure, and the cryptography is really secure, you can break through the system, through an automated access control system into some country. If you just break the access control system, put in an exploit, and what's doing? Oh, this exploit is only jumping to the part where the gates open. So we have a golden entrance for all automated inspection systems. Okay, let's shift to questions. If you have any questions. Yes? Oh, I have one of this cage with me, but no one is brave enough to bring his passport to me. So if someone is interested, he can get these cages after the demonstration here. These are the specific things, and I'm just putting my one also back just in case. Yes? No. Yeah? Okay. So the basic access control has nothing to do with the stored data on the RFID chip. The basic access control is used from the program loader to grant access to the machine, and I can just personalize any key, any desk key for basic access control. So it's possible to get someone else signed passport as a blob, using something completely different for the basic access control and put it onto an RFID chip. So you can use your old passport to upgrade it with the old printed MRZ to a new passport with basic access control. And we can personalize it, and we can just change the basic access control. It has nothing to do, and they are not checking the basic access control data and the key against the stored MRZ on the passport. There are 2 different things. Any more questions? Okay, thank you for your attention.